welcome to this webinar. This webinar is gonna be about an hour and a half. Correct me if I'm wrong, Makota. It's a demo webinar on tracing capabilities in the frame of the Assured project. The Assured project is a Horizon 2020 EU-funded project which lasts 3 years, and we are now in the last year of the project. This webinar is going to be recorded, and you're going to get a recording of the webinar probably shared afterwards by Margota, my colleague. I am myself the project coordinator of the project, and we have different colleagues here. We have many from NVIDIA, Dimitris from Ubitech, Stefanos from Ubitech as well, and Ahmed from NVIDIA. And I guess you will be able to drop your questions in the chat during the webinar. Don't hesitate to put any question you may have, and we'll try to address them at the end of each session. On that note, I leave the floor to maybe you, Dimitris.
Hello, thank you very much, Jean-Baptiste. Hello, everyone. I am Dimitris from Ubitech, and I will begin with a general presentation of the Assured project and the positioning of tracing mechanisms within the project. Thank you very much, Margota, Jean-Baptiste, for organizing this webinar. So I'm going to share my screen. Okay, so is everything okay? Can you see my screen?
Not yet.
Not yet.
Not yet. Okay. Okay, one moment.
No problem. Okay, it's loading.
Yeah, go ahead, Nabi.
How about now?
Perfect.
Great. So, hello everyone. So, as I said before, I'm going to start with a with a general presentation of the Assured project in general, and after that, the positioning of the tracing mechanisms within the Assured project. So, first of all, some words about the background and motivation of the Assured project in general. So, the core motivation behind the Assured is as the demand for increasingly autonomous cyber-physical systems increases and the need to address the needs of large-scale ecosystems and systems of systems, we need to provide certification mechanisms during runtime, and existing mechanisms towards validation require exhaustive offline testing of every state scenario. So the goal here is to provide security and privacy guarantees for the devices participating in such systems during runtime, as well as the system as a whole. So according to the ENISA threat landscape report, which you can see on the bottom right of the screen, the threat landscape affecting such kind of systems is rapidly evolving. You can see a difference between the threats affecting such systems in 2017 and 2021. And these, so we need to provide services that address these kind of threats, such as to ensure the trusted execution of insecure components. We need to safeguard code updates against tampering, and we need to ensure firmware and software compliance to execution policies. So in this regard, the goal of Assured, which is actually being completed as we're nearing the end of the project, is a development of a complete security framework that can provide operational assurance to large-scale systems of systems that consist of multiple heterogeneous devices with different security and privacy requirements. So the goal is was to establish a trusted service graph chains in such systems of systems, which addressed security, safety, and trustworthiness levels for mixed criticality services. Another important point to note is the adoption and the implementation of the zero trust principle, which essentially means that nothing is trusted by default. So we follow the never trust, always verify for assuring vertical trust for all devices comprising the supply chain. So in this context, in Assured, we have investigated various technologies both from a research and an implementation standpoint. First of all, it's enhanced operational assurance, which entails the execution of real-time tracing capabilities on devices without impeding their performance. Next, we have risk assessment schemes, which entails the identification of risks and vulnerabilities in the system for the entire service graph chain, which can affect the safety of the entire system. Next, threat intelligence information sharing, which refers to the secure and auditable sharing of all operational attestation data, which is essentially the output of the attestation schemes implemented as part of Assured, which is used for certification purposes. Next, we have decentralized identity management, which refers to the management of the identity of users and devices using the trusted computing-based wallet. Safety zones detection, which refers to the optimal deployment of the attestation policies used to move for the mitigation of these threats and vulnerabilities. And finally, the vulnerability analysis, which entails the protection of cyber physical systems through attack path analysis in order to afterwards construct the optimal set of attestation policies to be deployed. So in this regard, we have designed and implemented and integrated a wide variety of components. First of all, the attestation enablers, which are control flow attestation, configuration, integrity verification, direct anonymous attestation, mainly, which are lightweight attestation capabilities that are able to perform orchestration of the various attestation tasks. Next, we have the runtime tracer, which will actually be the focus of today's presentation, whose goal is to collect attestation evidence from the devices, such as control flow data and configuration integrity data. And the goal is, the innovation is that this is designed to be non-intrusive in a way that does not affect the performance of software performance. The SSI wallet, whose goal is to protect the identity of the device under a hardware-based DAA key and merge the concept of self-sovereign identities and trusted computing benefits. Next, we have the blockchain-based, the blockchain infrastructure, which has various purposes, some of which are the deployment of attestation reports following attestation, the execution of attestation mechanisms, and the sharing of threat intelligence data so that it can become accessible to certification and authorization bodies. Next, we have the risk assessment scheme, which is for the identification and the calculation of the risk and the interdependence graphs. And it's important to note that this considers both security and privacy, and also performs attack path calculation. Next, the policy recommendation engine, which receives output from the risk assessment engine in order to solve a constraint optimization problem to extract the optimal set of attestation policies. The security context broker, which acts as an intermediate component that bridges interactions of the devices with the blockchain. And the attack validation component, whose purpose is to receive the output from the devices following the execution of an attestation policy in order to identify new attacks, risks, and vulnerabilities. Also, we have envisioned 4 use cases where the system was tested. First, we have a smart manufacturing system where we have collaboration of industrial devices and human workers in a manufacturing floor. And the goal is accident prevention so that no harm is caused to human workers by the devices and machinery. Next, we have the smart cities use case, which entails the use of smoke and gas detection sensors and CCTV cameras in an urban environment. So here it is important to note that we have strict privacy considerations for the users. The smart aerospace use case, which includes the secure communication of aircraft with a ground station, including the deployment of secure software updates. and the smart satellite use case, which includes the collaborative execution of safety critical operations between satellites, as well as the communication of the satellites with the ground station in order to deploy secure updates again. So as we said before, here the focus of this webinar will be on the tracing mechanisms. So the use of tracing is most in the context of the use of attestation mechanisms. So when we say attestation, we refer to the methods with which a prover device is able to authenticate the correctness of its configuration state or the execution of software processes, which is performed when a verifier device issues an attestation challenge and an appropriate response is given to the verifier by the prover. So in order to provide this response, the prover device has to collect traces from the execution of the device, and these traces have to be sent, collected attestation evidence, in order to verify their correctness by employing the appropriate attestation mechanisms. So the assured runtime tracer as a component is able to perform near real-time low-level code inspection and tracing to collect raw trace data as attestation evidence, and in order to capture the requirements of assured with requirements to precision, efficiency, and transparency of the attestation. Okay, so next we have the types of tracing in general in the state of the art. We have software-based tracing, which is a purely software-based approach that does not require any additional hardware. There is also hardware-based tracing, which requires external hardware extensions to common processors in order to enable control flow tracing in parallel with the execution of a program, and hardware-assisted tracing that does not require dedicated hardware, but requires the presence of appropriate hardware tracing features, for example, using an Intel PT or an ARM core site architecture. So here we note that each of these tracing methodologies has benefits and disadvantages, such as that the software-based tracing does not need access to additional hardware, but is less computationally efficient than hardware-based tracing that does need external hardware, but is much more computationally efficient. So the approach that we followed in Assured is, given the state of the art, to create a software-based tracer with optimized design and implementation in order to provide somewhat equivalent performance with a hardware-based tracer, which is not really possible, but we aim to achieve this as close as possible. Also, the basic parameters considered in the design of the tracer are that first question is, do we need to attest the entire code base of the program in an embedded system? And the answer is no, because in Assured we perform property-based attestation, so we are only interested in tracing specific properties and functions. Next, we note that while the tracing per se process is efficient, the most significant part of the computational overhead is in the decoding phase, which is essentially the semantic representation of a graph in a way that makes sense and can be translated to the execution. So here the question is, what level of granularity in terms of attestation information do we need? And finally, we perform evaluation and comparison of this tracer against the software-based tracer against hardware-based tracer, and specifically using the ARM core site architecture, which has been implemented in Assured. So the approach we followed in Assured, based on all the above, is to provide purely software-based tracing, which is capable of high level of detail and accuracy in tracing of system functional properties, without requiring developers to change the executed programs in advance. In addition, we implemented hardware-assisted tracing capabilities whenever they are available in the processors, in order to efficiently recover information that's made available by the hardware. Okay, so a brief overview of the device architecture with regards to tracing. An important component and the prerequisite is the existence of a root of trust, which in our case is a trusted computer platform module that is used in order to assert the authenticity of the traces. Next, we have a trusted execution environment, which is an isolated execution environment that where the tracer is executed. We also need a TE capable processor, which is a processor that is capable of supporting the such trusted execution environments, and a hardware tracing capable processor, which needs to be able to support hardware-based tracing and to store control flow event data in a dedicated memory location. Okay, so having seen the architecture, we can move on to the a high-level overview of the tracing workflow. So in each device, we have an attestation agent, which essentially acts as a gateway between the TPM-based wallet of a device in order to receive the attestation policies from the ledger. So the attestation agent extracts the properties to be traced and triggers the tracer to initiate the tracing operation depending on what type of traces are needed. Then, after the traces are collected, the attestation agent verifies that the traces have been signed correctly and signs them with the attestation key. And then these are sent to the verifier who verifies the signature and performs attestation logic. Okay, so some words about the software architecture of the tracer. So with regards to the software architecture, it is split into a secure world and to the insecure world. So in the secure world, we have the secure storage, which is a configurable memory region, which is intended to store software control flows and runtime configuration securely. Next, we need to provide the signing operation, the secure signing operation on the traces by the TE using the private key. The capability to decode the control flows for hardware-assisted control flow tracing, and the ability to perform memory forensics on runtime integrity measurements to execute processes in edge platforms. From the insecure world part, we have the communication agent, which runs a REST service, which is responsible for the communication between the TPM and the runtime CFA and CAV requests. Next, we have the software control flow agent, which is responsible for extracting the visited basic blocks of the control flow and sending them to the safe storage. And the hardware control flow agent, which uses ARM core site tracing to extract the visited blocks of the trace application and to pass them to the safe storage. And finally, we conclude this presentation with some open topics with regards to tracing that are essentially subject for research topics. So first of all, is the latency of hardware-assisted tracing in order to alleviate the performance impact of decoding, disassembly, and analysis of the software-based components of ARM core site and Intel PT tracing. Next is the kernel-level CFA tracing, which where the verification of the integrity of the execution of a kernel is an open problem. Next, we need to focus on concurrency issues, where in Assured we focused on single-threaded processes, but optimizations can be made for the tracing of multi-threaded programs, which may induce a higher performance impact. And finally, CIV tracing with invalid sections, so which essentially refers to some challenges that are referred to the tracing of static files, which may be caused by changes in values in the memory due to dynamic loading of position-independent code sections or pages that are fetched on demand. Okay, so thank you very much. This concludes the presentation, and I will now, so as we are a bit tight with regards to time, I'm going to immediately pass the floor to Ahmad Atamli from NVIDIA, so he can give us an introduction to tracing. As always, any questions, you can write them in the chat so we can address them at the end of the webinar. So thank you very much. Ahmad, I'm passing the floor to you.
Thank you. Yeah.
You are in presenter mode. Swap the display. Perfect.
Hello, everyone. My name is Ahmad Al-Hamdi. I work with many on the tracer architecture. And in the first part, I will be talking about tracing, what it is, motivation, what do we aim to collect, I'll give you some 10 to 15-minute overview, and then many will talk about what we implemented and how we make this new innovation happen. So just to start where we started with this entire project and how it led us to kind of look at tracing and to what level. What started this road is, if you look around in today's world, there is really different type of malicious entities that basically end up attacking your system. Once an attack happens, they're either a virus that go about infecting other file in your system, either try to infect other machines that's connected over the network. There are more sophisticated type of malware like rootkit, which try to hook during boot time, during kernel time, as part of the firmware. Different stages of the boot to kind of get better hook and hold of your system. There are keyloggers that steal your information, everything, every keystroke that you write. Trojan horses that misrepresent themselves and appear to be good and basically spy on the user. And all these things, these malicious entities are things that we've done in the past and been out there for the last many years and so on. But what we've been seeing in the last few years that attacks are getting stealthier and beyond basically the traditional malicious entities that I'm presenting in this slide. For example, what we call as a fileless malware or stealthy malware, what used to be back in 2015, 5% of the malware out there that people use when they attack system, this kind of like quadrupled in today, 2022, 2023. We're seeing a lot more type of malware that basically does not manifest in the file system, and it has much more of a stealthiness to it. And what do I mean by stealthiness to it? It goes about hooking to the memory, avoid basically being detection by traditional security solutions like antiviruses, anti-malware, another type of intrusion detection system by just hooking to the memory. So the traditional security solution as we know them today are not really sufficient in order to analyze attacks that are happening in today's environments, whether it's a cloud, IoT, or anything else. And we need some sort of a new primitives and new things to go about analyzing attacks and malware in systems. And for that, we need to think about what kind of information we need to go about collecting. And with this kind of information, it will lead us to understand if there's some bad entity that is running or someone affected the execution of the application. To that end, talking about what exists and what you find the solution off the shelf, we'll look at three solutions that are available mostly today, whether it's commercial solutions on devices that are IoT devices or cloud environment or desktop. So this is what you're seeing here on the right side. This is basically what we've been doing for the last 20 years. This is old. This is something that doesn't really give you any idea about what's happening during runtime. When we're looking at a file system or a network, we have no notion of behavior. We cannot tell when did the attack happen, or how did that change the execution of a specific application or the operating system or what so on. These solutions, speaking about stealthy malware, they are no longer valid and they are failing behind in providing the protection that we need and cannot deal with this type of stealthy malware. This basically right away leads us to move into the right side, which is a kind of more execution-based, behavior-based approach where we can collect data from the system, And based on that, we can infer the behavior of specific things of interest. We can get about our weak point that we cannot solve by prevention, but can basically detect some malicious behavior or weaknesses in the system, and from there we can improve. So for the last basically 5, 6, 7 years, probably we've seen more and more basically solution that's coming to look at the memory. And the memory basically is what we call the arena. This is where the fight between good and evil happens, between the malware and your intrusion detection system happens. And looking at the memory or looking at the execution time, we can basically infer a lot of information. From that information, we can basically base our own analysis and see the behavior of an application and the system. On these slides, I will explore basically if this is still enough, because that's still kind of like give you an idea of the execution, but what kind of granularity do we want to get about the system and its execution really varies. And depending on the kind of data and metrics that we want to collect, what we want to trace, we'll see kind of like an innovation in place that would allow things to happen. And whereas basically we see that the innovation is going in order to provide the next level of tracing basis. Okay, so all this story, I talked about memory, but let me tell you about the paradigm basically that started all this back in 2003, actually, by a research paper by a researcher called Carl Griffin. And he came and introduced basically the concept of a virtual machine introspection. And back then, virtual machine introspection, literally as the name indicates, was analyzing virtual machines. And there were multiple approaches to analyzing virtual machines, depending on what kind of data. So there were virtual machines that were looking at the network, virtual machines that were looking at the memory, and basically the level of security in place based on that. And I wanted to work basically some of the things that Paul mentioned in the research paper is that the more we rely on the network, the less visibility that we have in the system. So the more that we want to kind of like get visibility into the execution on the behavior of the system, we want to kind of like move toward a solution where we're looking at the behavior. But he also mentioned one thing about where is this what we call an intrusion detection system, an IDS, reside. He said if the IDS reside in the network, then basically it has less visibility because we'll be looking at network packet, which really doesn't provide some sort of behavior. But if it's a host-based IDS, which means some sort of a solution that is running within a hypervisor or within a device itself, then basically it has more visibility. But the problem with that approach that it's susceptible to attacks, because we know basically the fight between good and evil, that they are sharing the same arena, the same shared resources, and one might attack another. That basically led us to the motivation of this kind of work that we are doing on tracing. Basically, how can we kind of get this concept of network, which is basically you are running out of band, where you don't have someone interfering with your execution, but the same idea, we want some sort of a host-based system that kind of like give you the visibility. And maybe we'll talk about that in more detail in the second part of this one. Okay, now one thing to talk about when we talk about the method for tracing. With virtual machine introspection, there's multiple methods that allow us to go about looking into the system. And with these different methods really varies the situation of it. We talked about host-based solution. With host-based solution, one of the problems that I mentioned in my previous slide is that I'm running in the same arena, the same shared resources that the malware is running on. So what does that mean for my security system? Now, for the first approach for virtual machine introspection, as we described in the literature, we have what we call this intrusive method. The intrusive method, that means if I want to look about and analyze a specific VM or specific application that I'm heavily involved in execution. So an example of this, some sort of a hypercontrol in a Zen architecture, if you're familiar with the Zen hypervisor, any execution that would require services from the hypervisor, including kind of like periodic look at whether the memory or a system calls or any of the metric that is being run by the virtual machine, this is being basically go back to basically to the hypervisor level, and the hypervisor basically have some sort of a VMI tool, and that basically go about inferring this. This is very intrusive because any operation that is basically being done by the virtual machine or the application that we define as sensitive is basically being intercepted by the hypervisor, which basically some sort of introducing some timing effect that the malware can go about detecting and trying to evade. This is then there's other approaches of saying, okay, other kind of like commercial solution where you have some sort of application that is running in the virtual machine, and you have another basically another kind of like piece of code running as part of the hypervisor, and there's some sort of a ping pong between those two to collect the information. This is intrusive. The reason this is intrusive because we require the user to basically install some sort of application, and second, it's in every part that relating the data and passing to the hypervisor, the user basically affected, which eventually affect the performance, and the malware can be fulfilled. With the non-intrusive method, still talking about memory without before moving ahead and what we want to do and how can we improve this. With the non-intrusive method, I don't really involve the virtual machine in the process at all. So what earlier I said about the non-intrusive method, looking at using like the hypercalls or some sort of an agent that collects information that's running from the virtual machine, we can go to an approach where the application is running. We don't need to intercept any of its operation, but in parallel, we can look at the memory that is being basically manipulated by the virtual machine itself. So based on some sort of a shared memory and CPU state, if we're running in the same machine and actually goes, we can basically access it in parallel, and for especially if you think about it as a multi-core system, and use one core for basically looking and tracing specific execution, then the virtual machine less likely to feel it. And there's still some sort of in a virtualized environment, what we call an observer effect. But for the most part, from intrusiveness point of view, it's not. Okay, so this does not interrupt any of the VM execution. This is running in parallel. The hypervisor sends information to the VMI tool, which is running on top of the hypervisor from a shared buffer, and the analysis happen over the memory by bridging the semantic gap between what is being from the memory to actual contextual information that we build from that. Now, so far I talked about memory, but it's really a more advanced method. We can infer things from memory, but we are still limited in what we can get. I mean, if I want to trace specific type of attack that is happening during runtime, and I want to look at actually specific path of execution within an application, then basically memory brings me thus far. It doesn't really bring me to the level where I can actually instrument some of the micro operation that is happening when within a specific application. And that's basically where CPU hardware extension involved, like using ARM Core site or Intel GT, that are basically integrated within the same package and the same die. It's available on that specific place, can be used in order to trace execution on instruction level, cache line level, and all that basically CPU. So memory thus far can get us to contextual information about the general of the system. If we want to take it to the next level and look at application level, something like a hardware extension is a must in order to provide the security guarantees and not basically to monitor. Okay, so with this, what are we aiming for? Behavioral model. We really care about benign execution versus malicious execution. Benign execution can be on a system level, where we can see that the system have all the right software components in place, the right configuration, and all that, to the level where we can say, okay, this is the application is expecting as I expected, which means something like a control flow graph, and seeing that this kind of like flow is as we expect. But we can also tag malicious execution with this approach and see we can blacklist some specific direction that we know that are bad in the application, and that can flag malicious activity rather than basically tagging an integrity violation. We believe this is quite valuable, and when we're looking at the next generation of malware that is looking to evade the traditional security solution like virus malware, ransomware, zero-day malware. But in particular, for the Assured project and our focus on, we took all this concept of tracing, whether it's a system tracing, application tracing, for the purpose of benign execution, malicious execution, and we connect it to attestation. At the end of the day, we don't want only an IDS. We don't want an intrusion detection system to detect if things are good or bad. We want to be able to kind of like relay this back to the user. That is the specific sensitive workload that needs to guarantee its execution. With the user will be able to know that this flow and this execution was attested and good and was not manipulated. All right, talk enough about the mechanism for tracing intrusive versus not intrusive and good versus evil. What does that mean? So in the system level, what do we need to collect in order to say the system is good? We are tracing things like running processes. Is there some sort of a process that spawned out of specific network connection that now I flag as bad? This is very common if you are connecting to any website and there's some sort of a split, specific download that you have. Suddenly you have A.exe as a running process where you never expected it before. So this on the system level, things like running processes, loaded kernel driver, the kernel itself, if there was a downgrade or a change of its binary. These are things that we aim for in order to trace the system execution and tell if it's in a benign state or in a malicious state. But take it to the next level where we're looking at tracing the application. We're looking at things like the control flow graph, where we collect all the good control flows for specific application, and we can attest it. And again, to a remote user, this is was executing the CPU state. This is kind of like another advanced metric that we can get using some hardware extension and say if there's something that is flagged, like for example, some advanced solution if you're trying to look for side channels attacks, looking at some CPU states and the execution path, whether it's acquired branches or something else. So our vision for what we are aiming for and the solution that we will be talking about in the next slide is that we basically discourage from using synchronous system breaking because it has multiple disadvantages like observer effect, system prompt computation, then infected machine, changes to system API, which eventually complicate the system from deployment point of view, performance point of view, and security point of view. What we've been looking at is the least intrusive method using asynchronous tracing, which means you don't really necessarily need to kind of go through about changing your application, your hypervisor. This is some sort of a separate module that can run either on a hardware device, either in an isolated environment like trusted distribution environment and so on. Does not require any involvement from the effective target, meaning that the application has stealthy execution because it does not share any resourcing. The data being collected through some hardware measure and saved in a private memory for the introspection kind of like software, and it has more visibility into CVE state. Like we can provide the instruction execution, the program counter, the flow graph, and any of those CVEs will work. Now, this is my part of this. I would ask you to give you how the tracing happening when you close the IP, what you do.
Thanks. Let me share my screen.
Yes. Thank you very much, Ahmed, for your presentation. Okay.
Okay. Is it on?
Yes, it is on.
Okay.
Thank you very much, Manny.
So thanks. Okay. So thanks, Ahmed, for the introduction. I'm Manny. I'm part of the team here in NVIDIA, is working as part of Assured on the runtime tracing, and I'll be happy to present what we did so far in Assured. So to connect back to what Ahmed had presented, in Assured, we're looking at system of systems deployed on premises, on user premises, running in edge devices, interconnected among themselves, and running critical services. Part of that vision is that these services may be written in memory unsafe languages, such as C and C++, which is very popular when thinking about resource constraints, edge devices as used in Internet of Things. This type of memory vulnerabilities can include, for example, buffer overflows, which can later be used to mount different kind of attacks, to hijack the execution of the programs, or to create different exploitations, tampering with the integrity and confidentiality of users' data. And the vision in Assured, as Ahmed presented, is going towards detection rather prevention, observing that preventing everything is very complicated and also comes at a very high performance cost. And detection specifically is extended towards attestation, runtime attestation reporting to relate to the third party whether the service behaved in a legitimate state or in some what's corrupted and exploited to run some malicious payload. And this brings up first challenge on the design of how we're visioning assured devices to run their software with, which is how to maintain secure detection even after an exploit has been mounted, which could corrupt the entire tracing infrastructure. So to that end, we envision the trusted computing base, or TCB in short, for edge devices, illustrated on the right. Let me go to the laser pointer. So for the trusted computing base, we're using an ARM feature, which is not prevalent only in ARM processors, but also in other commodity processors, which is a trusted execution environment. In ARM processor, this trusted execution environment is termed ARM Trust Zone, which is an architecture extension to create a trusted execution environment called a secure world, and the rest of the software can run in non-trusted execution environment called the normal world. So our TCB is very minimal. It consists of the secure world operating system, including the runtime tracer that does the detection and tracing of the critical services processes, whereas the rest of the software stack execute in what we don't consider trusted and can be compromised by an adversary. This includes user services, the operating system, the attestation agent, or other assured framework related services that communicate with the tracer, and also drivers like the entire TPM software stack. We do trust the hardware and the firmware, including the CPU, memory, peripherals, including the TPM, to be well designed and be part of the TCB. But that's it. That's basically the very minimal TCB that we assume for the edge devices. And this minimal TCB and using of off-the-shelf commodity features available in our platforms enables us to deploy the tracer with wide adoption. We're able to mount it in different kind of devices. And even when there is no ARM Trust Zone feature available in the edge devices, we're still supporting an ease of use mode using traditional isolation with the untrusted OS MMU configuration, and then the tracer runs in a isolated user space process with its own dedicated memory. While it's less secure than using Trust Zone, it still provides good security guarantees for using the MMU for isolation. Okay, let me go to the next slide. So how do we use Trust Zone with the tracer? So we are using OptE, an open source TE implementation for Trust Zone that has support for many different platforms. For example, in Assured, we're able to employ the tracer in both a Raspberry Pi 3 and a Xilinx platform. With OptE, the usage or the abstraction is towards a trusted application that you can see here on the right side. The trusted application implements the tracer trusted logic, and the API to communicate with the rest of the untrusted software is through the OptE OS, which communicates through the firmware with the OptE driver running in a normal operating system, and propagates back to an API, set of APIs working with user space applications. So with OptE, a user space application can open a session handler, and using this session handler, it can send commands to the trusted application, to the tracer, which the tracer then parses the command and the parameters that can be passed to it to execute the command and return the results back to the software that invoked it. And finally, the user software can also close this TA session. So how does it look with the tracer? So the tracer runs partitioned between the normal world and the secure world. The reason we are following this kind of a design is because we're seeing that the tracer has some parts that are not security sensitive, which we can put outside of the TE in the normal world, and some parts that are security sensitive that must be part of the TE and our TCB. This kind of partitioning allows us to further minimize the TCB and also enable very easy and simple communication with the other assured components running outside of the TE in the normal world, which means the untrusted tracer runs as a regular user process, and it communicates with the trusted tracer in the TE using this TA session handle and passing the parameters over shared memory, which is accessible to the TE and the secure world. And the untrusted tracer abstracts away all these TE manipulation details to communicate with the assured framework, with that station agent and user services using traditional Linux API, for example, with attestation server using REST API, a REST server exposed to that station agent. Whereas the trusted traces runs as part of as a pseudo trusted application, which means it runs as part of the TE operating system. The reason we're doing that is to provide the capability of the tracer to manipulate the trusted secure world MMUs to provide memory acquisition, as I'll discuss next. And also it provides the isolated security critical operations, as I'll also discuss next. And the tracer maintains the best practices for how to implement TE's communication, which is runs on an isolated memory. It copies the state back and forth between the TE and non-TE memory to avoid time of check to time of use attacks. It uses isolated OS services, depending on the world it runs on. So the untrusted tracer runs normal world OS services. The trusted tracer uses OptE OS services. And finally, all output that is considered secure sensitive is signed towards verification. So what the tracer does is tracing for control flows. The reason to trace for control flows is that they can hijack the execution of applications. For example, you have here an example on the right, an overflow attack, for example, a buffer overflow that overrided a function pointer, specifically the return address, and the arguments to it to execute essentially a shell process, giving full execution privileges to attackers. These kind of attacks are predominant in memory unsafe languages such as C, and it's the basis for different kind of attacks like returning to libc, ROP, JOP, and CORP. Oops. Can you go back? So this is not the only type of attacks that can be detected using control flows. Data-oriented programming attacks can also be detected. So consider the figure on the right again, where there's a number, some value, not a code pointer, that is data dependent on branches. For example, if the number is bigger than 0, execute some code, otherwise execute some other code. If an attacker is able to compromise this number and change its value to be positive or negative, it can affect which code is being executed. And by tracing the different code basic blocks that are executed, we can detect even data-related attacks that affect the control flows. And that's exactly what we're doing. So we're tracing the control flows of programs in the normal world in basic block granularity to even enable detection of data-based attacks. And the result is an ordered list of basic blocks, as illustrated here. Here is a set of each basic block is represented by its virtual address. And we can also emit debug symbols, even though currently the verifier does not require it. So in this example, we don't emit any debug symbols. And then as an example, just to illustrate how the control flows would look. So consider this greatest common denominator implementation that checks based on the input whether runs recursively and checks whether the current denominator is equal to 0. If so, we're done. Otherwise, compute the reminder. This is the Euclidean GCD implementation. So assuming we're starting with A equals to 3 and B equals to 2 with GCD, then the first basic block that we're executing is the entry. Next, because B is not equal to 0, we'll execute this block, which is logged. Next, we'll jump back to the entry. Afterwards, B equal to 1. So again, we're going to this B not equal to 0 basic block. We'll jump back to the entry, and then B is equal to 0. So we'll conclude with the final block of returning A equal to 1, which has the common denominator. And these are the basic blocks that we visited as part of this execution path. And this is what we're essentially reporting back as the traces for control flows. There are different ways to do that. There's software-based techniques and hardware-based techniques. Software-based techniques are divided into static versus dynamic rewriting techniques. With static techniques, it's usually more efficient than dynamic ones, but it limits interoperability. For example, you need to statically rewrite libraries for processes that you want to trace and maintain some non-rewritten version of these for programs that you don't want to trace. It requires manual modifications. Hardware also is divided into hardware-assisted versus dedicated hardware. Hardware is usually more efficient than software-only approaches, and as we'll see next with what we are doing with ARM Core Site. But it limits usability and adoption because it relies on dedicated hardware that supports these features, and dedicated hardware, unlike hardware-assisted solution, further limits the usability and adoption because these kind of hardwares are very hard to come by. So that's the way that we're doing it for the software-based solution in Assured. We're essentially rewriting the prologue of each basic block. So we added a red rectangle here at the top to illustrate that. This rewriting is based on the Dynamo framework, which, as its name suggests, does dynamic binary rewriting. And essentially, this prolog that we add on top of every basic block logs the initial address, the first address of the basic block, representing the basic block itself. It logs it into a thread local storage buffer. And once the buffer is filled, we're sending that specific buffer context to the trusted tracer. The trusted tracer stores the buffer's content in the secure world in a ring buffer. We're using a ring buffer to make sure that even if we trace more than our memory allows us to trace, we'll never run out of memory. As long as the attestation agent sends tracing requests frequently enough, we can send the latest control flows without overflowing this ring buffer. And the tracer also signs the traces before sending them back through this OPTI-based interface. So how does the signing work? So the tracer signature scheme is very complicated. We assume a private key is embedded in the tracer. This is only available to the secure world. And while we could have just signed the traces based on this private key and send them back to the attestation agent for verification with the public key, we're also doing a communication with the TPM to further verify the traces. So the tracer generates the traces and signs a hash of them together with the pre-requested knowns. And to delegate the trust to the TPM can verify the traces signatures and sign the traces further with its own TPM private key that enables the verifiers to verify both the tracer private key and the TPM's attestation key, which enables more secure remote attestation-based solutions. Unlike the software-based approach, to use CoreSight, we have to actually program the dedicated hardware of CoreSight. And specifically with CoreSight, we're using the embedded trace macro cell feature of ARM, or in short, ETM. To program it, we're programming a buffer to work in a FIFO mode. So when it overflows, it similarly to the ring buffer we have in the tracer, overrides all the traces. We're also programming different registers to control how tracing is enabled and disabled, and flashing of the buffer. This includes the status register and control register, and we're using the read and write cursor registers to dedicate when the buffer might be filled to flush it before it ever gets filled. This register essentially manage a state machine, starting with a stable state, moving to a running state where the tracing occurs. Once we want to drain the buffer, we're moving the tracer to a stop state, and then draining the buffer towards sending it to the secure world. So it looks something like this UML figure. So the untrusted tracer enables the tracing with the buffer. The program under trace updates the buffer. The tracer polls for whether the buffer is filled. Once the buffer is filled, it disables tracing, pauses the application, and drains the buffer. It then passes the buffer to the content to the secure world. And then similarly to the software-based tracer, the attestation agent can request traces. One difference between CoreSight and normal software-based tracing is that CoreSight is further encoded in an ETM format. So before sending back the traces to the attestation agent, the tracer must decode them and reconstruct the exact execution path, and also generate the proper traces format and sign them. Finally, we're also configuring the CoreSight traces to trace only user space programs, much like the software traces. And we're filtering based on address ranges and the process ID to only trace critical service programs that we're interested in tracing in Assured. The decoding phase that I mentioned earlier looks like something like that. CoreSight emits a binary format that can be decoded into a set of addresses and atom packets. Addresses are elements in the trace stream that indicates an address starting from that specific direction, which can be inferred with other type of packets like atom packets. Atom packets are direct branches that represent taken or not taken decisions. So to reconstruct the exact addresses of every basic block, one needs to first disassemble the program. For example, here, it's a disassembly of the program. It starts from the address 900, which is main. Next, there's an atom packet for E, which is taken. So we're searching for the first branch instruction, direct branch instruction. We're finding that the branch instruction is for branching to the loop function, and it's taken, so it means that the flow indeed went to the loop function. Then there's a bunch of taken branches that jumps back to the loop until there's a not taken function, not taken branch, which means the flow continued up to the return instruction, which demonstrates that you returned back to the main function after the loop function. So that's how we are doing this analysis with the disassembly to reconstruct the exact execution flow before generating the traces and signing them. And we're using PTM to human to do the call side decoding and the capstone disassembler to do the binary disassembly. So I mentioned all of that to say that hardware is more efficient than software. So to demonstrate that, we've measured the tracing overhead over the EMBench IoT benchmark suite. And we saw that even for all the different kind of applications that are part of this benchmark suite, the core site traces have very similar performance or very negligible overhead compared to the native execution, which is not traced. The software-based solution, however, adds orders of magnitude overhead, which, while have easier adoption, can, due to lack of requirement for hardware availability, adds some overhead to the tracing. Further, the tracer supports runtime configuration tracing. So this is inspired by the integrity measurement architecture in Linux that enables a chain of trust to measure files before they are accessed or executed, storing them in a kernel list, in a kernel memory, or even extending them to the TPM and later testing them. And the key idea is to enable runtime integrity tracing for the memory processes loaded in memory and not just files stored on a storage. So to do that, we measure the in-memory processes and libraries, and it enables us to mitigate memory-only attacks and not just storage attacks. The tracer, again, runs on the secure world, and it can access the main memory. And the programs execute in the normal world, and they also access the main memory to store their intermediate execution state. And upon an attestation agent request, including a process identifier and a list of invalid bytes, which I'll discuss shortly, the tracer can then generate an in-memory representation of every code page relating to the program and its dependent libraries. The way we're doing that is based on retrofitting VMI techniques, virtual machine inspection techniques, and memory forensic techniques to analyze critical OS data structures, inferring the exact location in the programs, the virtual address space of the programs, where the code pages are located, and then computing a hash per each one of them. There are a bunch of challenges we had to overcome to support this. First, how to access the memory from the secure world. Second, how to handle pages that may be unmapped. And finally, how to get the reference attestation value at the first place. So to overcome the main memory acquisition challenge, we found that in OptE, when we run as a pseudo-trusted application, we can use the fact that we're running as part of the OS to manipulate the MMU hardware to map normal world pages for read access for the tracer. And using that, we were able to acquire the memory. For the OPTE deployment mode of the tracer, we're using a kernel module to expose similar functionality while still maintaining the same set of tracing capabilities. Second, to solve the challenge of how to get the code pages, we're relying on kernel symbols virtual addresses. And for storing them securely in the tracer, we're embedding them in the secure world itself. And thereby we're enabling page table discovery and physical to virtual addresses translations implemented specifically for the ARM architecture. And we're also enabling accessing to specific memory regions and not the entire memory to infer the exact semantics of where the code pages are located, which libraries are mapped for which processes, and reading them towards hashing them. To handle unmapped pages, the tracer pins the traced processes pages in memory, so we don't have to worry about unmapped pages having incorrect hash result. And finally, to get the reference attestation value, we're computing all the offsets that may be legitimately changed. For example, using the dynamic loader to correctly employ procedure linkage table and global offset tables, and computing these offsets a priori and ignoring them when computing the overall hash for these pages. And finally, the tracer computes a reference golden hash based on these invalid offsets and ELF-based parsing. So to put it all together, the tracer runs partially in the normal world, partially in the secure world, abstracting away these details of how to communicate between the TCB and non-TCB. It traces programs and communicates with the trusted tracer to do either control flow tracing towards control flow attestation or runtime configuration tracing towards configuration integrity verification in the assured framework. And I'll now present a short demo to showcase how it looks like. So I'm running the tracer right now in the normal world, and to access the memory, I need to load this kernel module for accessing the memory. And to set up the symbols in the tracer itself, we implemented a symbol extractor kernel module that extracts the kernel related symbols. Loading these symbols into the memory, you can then read the symbols from the kernel log and embed them in the tracer itself. To make sure that the symbols and the memory acquisition module were both set up correctly, we implemented a very simple memory forensic plugin to emit the active process list from the tracer itself without communicating with the OS. And you can mount it by running the tracer. The tracer is this Linux tracer and with the test argument. And you can see that it executed and emitted all the processes in the system that are currently active, including the Linux tracer that was running while it was executing. The same flow also works on OPTE. So for example, you can see here a deployment in a Raspberry Pi, where the upper part of the screen is the console for the secure world, and the bottom part of the screen is the normal world. We can similarly invoke the tracer with the test argument, and it will emit all the active processes in the system, including the untrusted tracer part called OPTE tracer in this case. But the trusted tracer part is not emitted because it's not part of the process list for the normal world OS. So let me jump back to the Linux-based tracer setup because it's easier to work with than working with a remote Raspberry Pi. So to showcase the control flow at this tracing, let's run the tracer. It runs as an endless server waiting for requests from an attestation agent. And we're also implementing a very simple application that just does calls to different functions. And to run the tracer, sorry, let me do it like this so I can see the spider bar hiding the top of the screen. So you can see that when we run this test with tracing, we emitted log for the tracer to output the basic blocks and also configure it to output the symbols for the sake of the demo. And you can see that main indeed calls foo and then returns back to main and then calls bar and then returns back to main and then returns back to the start of the loop and so forth until the program exits back. And we can also change the flow of the program to run endlessly to showcase how the attestation agent can ask for control flows from the tracer. So we can compile it and run it again. Now the tracer will continuously get control flows, and it's a ring buffer, so we don't have to worry about it getting filled. And you can send attestation agent request using a REST API, using the request Python interface to send it. And we're sending the control flow request for the tracer with the value of the program's name. The first result is always empty because it set up the process identifier to trace. The second result will print the latest control flows that are part of the tracer. And we can continuously do so as long as the process is alive. Once we terminate the process, we will not get the latest control flows because no process exists right now. So we'll get an empty result. For configuration integrity verification or configuration integrity tracing, we can also showcase that. So first we need to generate the reference attestation values for a test application. The test application has two libraries that are linked to it, libc and ld. And we're also measuring, of course, the hash values for these libraries code pages as well to detect attacks on libraries, on not only processes. So to run the CIV trace, we first run the Linux tracer, and then we were sending the tracing request using the reference values we generated, and specifically the invalid offsets in these reference values. But the first result is 0 because I didn't run the test. So let's run the test and rerun the request for configuration integrity tracing. And we can see that now the tracer indeed computed the hashes for all the virtual addresses of the libraries. But the hash isn't the same as what we computed for the golden hash. And the reason is that we didn't lock the pages in memory. So we computed hashes for pages that are unavailable, considering them as 0. So we're having different hashes computed. So to fix that, let's spin the pages. So we have a tracer script to pin the pages in memory. It receives the process name. Once we execute it, we can see that it succeeded. And if we'll run the tracing again, we'll now get the correct result for all the libraries, comparing them to the reference value. Okay, and the last one. And finally, I'll showcase the core site tracer. So this is performed on the Jetson platform, Jetson TX2 NX platform. And the tracer, we first run the program without the tracer at all. It's just a CRC32 computation from the mBench IoT benchmark suite. So you can see that it took about 2.5 seconds to run. Now to run it with core site tracer, we'll first run the tracer, much like we do with the software-based approach. And to run the core site tracer, we're running the core site tracer to configure the buffers. And you can see that it finished very quickly. Whoops, it finished so quickly that it stopped. And you can see that the result was very similar in the orders of 3% overhead, which is within the standard deviation of what we measured. So that's it for the tracer. And thank you.
Thank you very much, Manny, for your presentation and demo. Very informative and insightful. So we are a little bit ahead of schedule. So if there are any questions for Manny, we can accept a couple now. Okay, seems like there are no questions. So I will pass the floor to Stefanos Vassiliadis from Ubitech, who will make a presentation on leveraging tracing for efficient attestation. Stefanos?
Hello, Dimitris. Hello, everyone. Can you see my screen?
Yes.
Okay, great. So I will continue the talk about the tracing, but now from a more trusted computing perspective of things. So for the assured framework, what we wanted to achieve is to basically add the tracer into our trust computing base. So for every device that it's running, it is enrolled to the assured framework. We have a TPM, and the tracer was originally running in the untrust world. So we had to actually converge, as many described, from an untrust application to a trust application using an OPTE. Basically, it's a trust execution environment that exploits the hardware capabilities of ARM processors, the trust zone, and then we had to find out how to semantic trust between the tracer and the TPM. So the reason for all this is because the tracer is actually responsible for monitoring everything that happens inside the device, because we consider every device that is enrolled to the framework is an embedded device that has one or two or three, basically a few binaries that are running, and we want to attest each one of them. So for this purpose, we actually have a pre-shared key between the tracer and the TPM, and with this key, we create key restriction usage policies to protect our TPM attestation key. For each invocation, we ask for the TPM to create a nonce value that is stored inside the TPM, and this is then stored with the tracer in order for the tracer to create an authorization hash, which is basically dependent from the trace hash, the extracted trace hash, and then sign it in order to be verified from the TPM. So as you can see here, this is the exact protocol with the specific TPM commands. Here we define the policy. The policy is based on the name of the tracer key. And then for every invocation that the attestation agent wants to do to the tracer, we create a fresh nonce that is stored inside the TPM. We ask from the tracer to extract the hash trace and sign his response, and then the TPM takes the response of the tracer, loads the pre-cert key, and verifies the signature with respect to the nonce value that was created inside the TPM. If everything is successful, then inside the TPM we have a representation hash that should be identical to the key restriction usage policy that we defined during boot up, bind it with the tracer's key. So all this happens basically, first of all, for the integrity of the traces, that the signing operation happens inside the trusted world, and of course for to prevent replay attacks. So we explored several tracing techniques. One is the eBPF tracing. The eBPF tracing is a fully software-based solution that is leveraging kernel hooks to monitor what happens inside our device. The Assure tracer, as many excellent described previously. The Intel PT, which is a pseudo hardware-based solution, but we have limitations here because it requires support from an Intel CPU in order to have this feature, and then the core side tracing, which is a full hardware-based solution. Here we did the evaluation as we did with the Assured tracer and the core side tracer with the embedded IoT applications, and we can clearly see that the Intel PT has a really efficient tracing. The overhead that is actually added to the native execution is really small, but the Intel PT tracing has a major flaw. In order to actually decode the results from the tracer, you need to pay a lot of time. As you can see here, in some cases, like in prime count, we actually go up to 150 milliseconds. So we gain a lot from just tracing, but if you actually want to make some sense from the trace themselves, then you have to pay a small amount of time. In comparison to our Assured tracer, here we had the evaluation again with the embedded IoT applications. We do observe a little overhead between the native and not and the traced executions of the applications, but here the version where we actually trace just the execution of the applications without batching the debug symbols and actually debugging them, decoding them, sorry, we actually get really good results, even in comparison to the Intel PT solution. If we actually want to have the debug symbols and from the execution, you can see here that we do have a lot of overhead, but this is not necessary because from our solution that is designed by TUDA, we don't actually need the debug symbols to perform a control flow attestation. Thanks from my side. If you have any questions.
Thank you very much, Stefanos. So Seems that there aren't any questions, unless anybody would like to make a comment. Okay, then. So this concludes the presentations for today's webinar. So Margotto, Jean-Baptiste, if you would like to make any closing remarks.
Yes, Dimitris. No, the only thing that I would like to add is that on the 4th of July, we have the last webinar on blockchain that will be held by UBTech with the University of Delft. Please stay in touch with us on Twitter or through the website. All the information about this next webinar will be published there as soon as possible. And thanks for joining us.
Okay, then. Thank you, everyone, for being here. Thank you to the presenters for their very good and informative presentations. And we will see you at the next short webinar, as Margotto said. Thank you very much.